going to talk about variational autoencoder. It's short for VAE. So, I mean, this is just some name we are going to touch a little bit later. But let me just talk about some general framework. So the general framework of VAE can be think into the follows. So there are some data here of X, which is our observed examples. Be like images, could be videos, could be sound waves, and like text, and for examples. Then of course, there are some like this X follows some distributions, P of X. But the issue is we don't know this P of X. So this is usually not known. So if we are known, we can just sample from this P of X. So, and what we usually do is we usually assume there is some like low dimensional later representation of this data of X. So that means I have some low dimensional representation of data, which is called Z. So this is low dimensional like latent representations. Okay, so the idea is instead of we trying to find out this P of X, we're trying to learn this low dimensional latent and the representations. So then, so once we, what does that mean? That there are some like, and functions that can map from this X into this low dimensional representations, which is the conditional probability that the end of the distribution of Z conditional given of X. So this has a name. It's called likelihood. Of Z given X. Okay, so this is also unknown. We don't know that. So this is also called encoder. That means I try to encode something that is complicated in high dimensional into low dimensions. So you can think about this X is living much higher dimensions. It's R and D, so Z you can think about maybe lives in small dimensions. R little. Okay. All right, so so this is encoder. So encoder, that means there's some like very high complicated and the data in like much higher dimensions and map it to some lower dimensions. All right, so and also, if we know everything in Z, it can map back X. So this is, you got the probability X Z. So this is the posterior probability. Of getting X given Z. And so this is called decoder. So decoder, that means if you are given a Z, I want to map back to the high dimensional data. So the philosophy is quite simple. If we can, instead of model, X, I actually want to build a model of Z. So if we can sample the data on the level of Z, then I can, and I can somehow learn, this like decoder and encoder by our neural network in a way that we can, and in some senses, we can sample this X and through the Z's. There's also one more thing left, that is the prior of which is the, you think about distributions of my latent variables. So this is distributions of my latent variables of Z. So you can think about prime as well. So usually, in almost all the settings, it is just a standard Gaussian. So you can think about we are actually trying to learn an encoder to encode a very complicated data set into at a relatively low dimensions, and such that my previous complicated and distributions becomes and standard Gaussians. Of course, all these encoder and decoders is not known. We actually need to approximate that. So this approximation comes with some like an parameterization family. So this is actually being approximated by Q phi and Z and X. So phi is some parameter. So you can think about these are all the weights in the neural network. This is also being approximated by P phi X. This is a family of the parameterized functions. So you can think about we're trying to use a neural network to trying to approximate these decoders. All right. So the fundamental idea is we want to compress like a very complicated and the data of X and into like in the lower dimensions and trying to learn this lower dimension representations. So like hypothetically, this is something that we don't know. Somehow we want to approximate this something we don't know by this parameterized families. So does this like decode. So that sounds a very difficult process. We don't actually know both of these functions. So I'm going to step back to think things a little bit different. Okay, so this is, I mean, if you took my classes on either machine learning or other and like stochastic process, we talk about Gaussian mixture models or hidden Markov models if you took stochastic processes. So this is a very typical latent and the variables and the structures in Gaussian mixture, and we have a latent variable which is the member of clusters. In the hidden Markov model, it is also a latent variable which is the hidden states. So all the philosophy, as far as you have this like and the latent variables, things just and then the tricks are very similar. So it involve all these kinds of like names. We're going to talk about this momentarily. But my goal is let's just focus on an encoder part. Is I want this thing is close P. So this is my goal. Okay. So I want this to be, and how close it is, and what does that mean? I mean, in terms of close, we are going to quantify that momentarily. So these are, and these you can think about. We have like either, so you can either think about this as like an parameterized family of functions or some like proxy distributions. Okay, so this is our goal. Another thing I want to talk about this is let's step back to think about this formula right here. Log of Px, which is my log likelihood. What I'm going to do is I'm going to introduce, this is basically multiplied by 1. This is integration of Q theta of Z given Z. So this is because this integration will give you 1. So I'm going to move everything. This becomes integration of Q theta Z given X of log of P of X dz. So this is basically, you can think about it, we are trying to take expectations of my random variables of log of px with respect to the distributions of q theta z given of x. So this is expectation of q theta z given x of log of px. Okay. So then we're going to use the Bayes rules. So this is equal to I'm going to introduce the latent variable back to z, but divided by pz given fx. Right. So and the logarithm, I missed the one. Right. So then, and what I'm going to do is I'm going to multiply one more term on the top and bottom. So I'm going to multiply q phi z given of x, z given of x. I'm still the same, just play the math tricks. Then I'm going to split things up. I'm going to keep one term here. Let's see. I'm going to keep one term here with this. Another term. I'm going to pick up. So I basically want to split this and the multiplications into two summations because we have a logarithm. So basically, this is getting expectation of q phi z given x. And the first one, I'm going to take this and this, which is the logarithm of p of x and z, joint distribution divided by this q z given of x, plus expectation of, right? I mean, so I'm just playing around the math bunch of identities here. Divided by p of z given x. Okay, so basically with all these math tricks, it split this term log of px into two terms. So this is my first term, this is my second term. So this whole thing has a name. Log of px right here, it's called evidence. It's just a name, it's called evidence. So it has a second, sum of second term and two terms. The first term, as I said, it looks like this. So this is called evidence lower bound, or short for elbow. Okay. The second term right here is actually the KL divergence. So this is expected z given of x and the logarithm of q theta z given x over p z given x. So this has an annotation. I'm going to write this way. It just means there's a KL divergence of these two distributions, which is q by z and a double bar of p. So if you know a little bit properties of this KL divergence, KL divergence has this following properties. If first KL divergence, I have a two distribution, which is Q and P. this is always bigger equal than 0. And P equal to Q if and only if KL divergence is equal to 0. And of course, I have to assume like this is P and Q is like in strictly positive. Yeah.
Good basic question. The expectation over Q sub theta of C given X. Let me ask it this way. That is an integral.
Yeah, right here.
Okay, great. Good. So it's over Z.
Over Z, yes.
So X is a parameter.
Yes. X in this integration is a parameter.
So X is a parameter in both the in Q and the
X and phi.
And the P. Wherever it appears, X.
Yes. Yeah.
Great. Thank you.
Okay. So this is like integration of
X. That's good.
Okay. So what does that mean? I mean, this whole thing of KL divergence is actually always bigger equal than 0. So this is bigger equal than this. I mean, I have like basically write everything this is equal to, as a short notation is ELBO plus KL. But we know KL is always bigger equal than 0, so this is bigger equal than ELBO. So that's why this, I mean, it's called ELBO because this term here is actually the lower bound of my evidence. So that's why this is called, I mean, evidence lower bound. Right. So, but that's good. But does that? I mean, how does that? I mean, to actually help to achieve my goal. So I want my PZ of n given x and the Q theta z given x to be as close as possible, right? But KL divergence actually can give a good quantity to do so. So if my KL divergence of these two distributions to be small, then these P and is close to P. So somehow, all we need to do is to minimize option 1 is to minimize my KL of this whole thing right here. But unfortunately, that's impossible. Why? It's because my PZ given X, and I mean, my likelihood is not known. So we don't know that of the ground truth. So that's not possible. So the option 2 is the following. This actually is the first trick. Then you think about it. First thing is because log of px here, once you're given a data set, and we know there is some latent and some hidden like distribution of p of x, it actually exists, but we don't know it. So that means my p of x right here is a constant, but unknown. Right, so this is basically the evidence is a constant, but unknown. We know the evidence is equal to elbow plus KL. This is a constant. We want to minimize the KL. Equivalently, what we can do is we can maximize the elbow. So like maximize elbow is equivalent as minimize. Like again. It turns out maximize the elbow will be significantly easier than KL. Although we still don't know what is the and the joint distribution yet. But we are going to build models on that. All right, so is it clear? So the goal to achieve this goal here is we said we want to minimize the KL divergence between these two distributions. But directly minimize the KL is impossible. As a result, yeah.
Do you say px is constant given a fixed x, or is it like for any, like the whole thing is just
so you can think about P, so the whole distribution is fixed but unknown. But X is one particular an example. For example, you take an image of a cat that this P of X, there exists the tiny numbers there, but we don't know the value precisely.
Thank you.
All right.
So is the context that we are taking a step to learn from one example?
Yeah.
You said X is a particular image.
Yes, particularly examples. Yeah.
So
yeah, you
go to all of this.
Yes, you have a bunch of data of X here. Right. So you say you have n like images that you have, but an odd image there are cats. So you want to generate a new image of cats that doesn't belong to this n images. So this is the goal. Oh, sorry. I think I should be more careful because I somehow assume this is already as mentioned, but this potential is not as mentioned. So given
so by training we have learned five, and now we are about to generate.
Yeah. So this is actually follows some like unknown distributions. I want to generate a new like data that actually follows. This is important, I think. So that's why this is called like in a generative AI, right? So this is I want to generate the new stuff out of like something already being seen and discovered. All right, so maximize elbow here. Okay, so then let's get so let's get this and then the whole like framework and write it down. So we have X. So we actually want to map into Z. This is the encoder. My encoder here is Q theta Z given X. Followed. Then Z I'm going to map back into X here. So this is process called encoder. So this process called decoder. So we haven't talked about decoder yet, just something I'm going to talk about this thing. It's actually called the distribution of PC. X given this Z. So this whole framework in neural network, it's called autoencoder. Right, so that's why this is called variational autoencoder. So, and why this is called autoencoder? Because this whole framework, and you can think about as I have, like this is like my neural network. So this is from X, and you map to like lower dimension of Z, then map back into X. This is called framework of auto. So everything like this black, think about this. And basically, like and the multi-layer perceptions.
So the kind of are we starting with an X and we process it to this and get a better X?
So I want to train this parameter of theta and phi, which is my weight of my neural network. So in the future, somehow I can like directly sample the Z, and I can regenerate this new images. Okay, so let's go back to elbow here. So this elbow is actually Q theta Z given X log of P of C joint distribution and Q theta C given X. Okay, so I'm going to use base and conditional probability one more time. This is P of X given C of P of Z. Fortunately, the first thing I already know, the P of Z is the standard Gaussian. So that's the first thing that we know. That's good. I mean, my prior distribution is actually the standard Gaussians. Then I'm going to split things up. I'm going to split up with, okay, so then we have seen this, this is my posterior distribution right here, P. And of course, we don't know that. So what I'm going to do is I'm going to replace this posterior distributions by my decoder here. So this is going to put theta. Right. So this is the first time actually shows up the theta here. And of course we want to minimize the elbow, so that means we also need to optimize for the P theta at the same time. So since we are trying to use this like decoder part here, so we have a P theta X and theta Z. So somehow we already know everything here. This is a neural network, this is also a neural network, and this is already known. Somehow we can, but like we still need to take that complicated and the expectation with respect to the hidden variables. All right, so that's a promising sign. So then I'm going to split things one more time. So this becomes logarithm P theta X given Z. Then the rest of things like this. So this is but nothing but KL divergence. It's like subtract of Q theta Z given of X with P of Z. And for this part, we already know this is the standard Gaussians. So each part actually has a name. So I'm going to talk about this a little bit later. But why this? And I'm going to just like tell you the name for now. You can see right here. This is I'm trying to calculate this expectations of log the X given on Z. So this is called reconstruction error. Well, that doesn't look clear why this is called reconstruction error or reconstruction term, but you will see this momentarily later. So this has a portion of the decoder right here. So this is actually focused on the decoder. And of course, right here, we still have like Q and Q5s going on. So, somehow the whole philosophy is I want to sample the Z actually follows the Q theta Z given of X. Then I'm going to evaluate this expectation by using sampling methods. And then we can calculate this whole expectations for this sampling techniques. The second term is called prior matching terms. It's quite clear, right? So, and this is prior. This is my my likelihood. I want to match my likelihood with my prior. So this is called prior matching terms. So this has something to do with encoding. Okay. So so let's just and write things a little bit carefully because, and right now it doesn't seem that clear. We can just directly use. I mean, it's already very promising, but that's still not the right, and finished yet. Okay, so here is my objective here. So let me just write here. So this is my objective to maximize. Right. Now we are going to tackle this expectation. So I'm going to approximate this and expectations by samplings 1 over L. I'm going to call this 1 over N because I have N samples, right? My 1 to the N and the log of P theta of X conditional on Z of I right here. But what does that the Z count? Z actually has to follow this distribution. It has to follow Q phi Z I of X of I. Because we only have a data of X of I, so we need to using my X of I to generate Z of I. All right. So that means we have the data of Xi. We need to use some specific method to generate my Z of I. Then we get a bunch of Z of I. Then we calculate this log of P thetas and average them again. Then subtract KL divergence of Q theta Z conditional on X given and the P of Z right. Okay. All right, so that means we have a two part and need to need to maximize part. So the first thing is the reconstruction, which is the first part. That actually is saying we already know my Z on my decoder part. Okay. So find theta to maximize my posterior distributions. Okay. So I mean during training, we need to make sure my Z actually follows the Q of phi of the Z given of X. So you need to sample these things, sample these. Then you will get a pair of X and Z's data set. Then you get this an X and Z data set. Then you're trying to find the theta to maximize my posterior distribution. So this is the first part. And also in the prior matching part, is the part that I have X, I have a Z. It's the other way around. So we want to find phi. I mean, here we have a minus sign here. So so the whole thing I want to maximize it. With the minus sign, that means we are going to minimize it. Minus the KL divergence. And of course, in this cases, we already know x, we already know y, so we just use the x and y's like direct. But the beauty here is for KL divergence. Okay, so I mean, there's next, and the next things I need to talk about. If you have a general Q phi z given of x, there's no way that you can find this phi and easily and with a simple ways. So this KL divergence for and the whole formula will be very, very complicated that you don't even know how to calculate this, for example. So so this whole thing is not trivial because if we stay and right here, we still don't know how to train these things. We still don't know how to train the whole things. That's why we are going to introduce the second trick. The second trick is going to call, I'm going to erase here. Reparametrization trick. So in rough idea, in all these generative AI, machine learning, particularly in deep learning, if you want to derive something analytically, you usually need to assume something is Gaussian. If something is Gaussian, there's a very likely chances you can calculate some analytical solutions. So if we find out something that is really difficult, usually what we do is we try with the Gaussians. So here is my assumption. So I'm going to use different color here. So my assumption here. So I have, I think I have only used one assumption right here, which is my prior is the standard Gaussian here. This is my second assumption. That means my encoder is actually a Gaussian, which is variable z, but it's a function of x, and assume my covariance right here is a constant sigma square times identity. And of course, you can make things really complicated. But here, the key complication is my mean and variances is actually a function of x. But it's okay. So so that means we are not trying to use my neural network to approximate my Q phi right here. This whole thing is really complicated. Actually, the reparametrization trick is I'm going to construct a deep neural network to approximate the mean and the variances of my Gaussians. So that means my mu right here is a mu of phi of x. And my log of sigma squared, it's something like. So you think about this whole thing as a neural network. Why we need to put a logarithm? And of course you can just put the neural network with the sigma here. But with the logarithm of sigma squared, then the value can go through from negative to positive. So it's much easier for neural network to handle because neural network cannot really handle very well with hard constraint. It's much easier to be handled with with the whole domains. Okay, so then this z of I actually follows this Gaussian distributions of mu theta of x of I and sigma theta squared x of I of identity. And everything here is actually approximated by a neural net. And of course, once we approximate everything with the neural net of the log sigma squared, you just check, I'm exponential of this values. If you know this, you immediately and find out this is really, really easy to sample of X of I, because in general, this is really, really difficult to sample arbitrary distributions. But with the one exception, which is the Gaussians. If you are given a Gaussian, this is really easy to sample. Okay, so to sample the Z of I follows this distributions, all we need to do is I actually need to construct a Markov chain to sample, and you can just sample this immediately. We can just call the Z of I is equal to mu theta of X of I plus sigma theta X of I times some, I'm going to call it W here. W is the vector, and the W here is actually follow a standard Gaussian distributions. So you throw a dice, sample a W, and follow standard Gaussian distributions. Then you just add them up. Then you can show this Z of I actually follows this Gaussian distributions. Okay, so that actually solves the first part, which is the reconstruction part. Right? We are not actually trying to, not the reconstruction. It's we haven't, and a part of the reconstruction part, because in the reconstruction we need to sample this Z of I here. We haven't talked about the theta part yet, but in the part of the reconstruction, we actually need to sample the Z of I. We have and tackle this sampling part, which is very simple. Okay, so this is the first part. But we are not done with the reconstruction, and I'm explaining why this is called reconstruction. And of course, like from this expression, that doesn't look like reconstruction at all. So then we have a second assumption. That, for example, there is some like decoder function here. Which is you map the Z back to the X here. And of course, you want this X to be close to my original X as much as possible. Then my assumption here is my X hat minus of X is actually follow a Gaussian distribution of mean of 0 and a sigma of decoder square. If you actually have this an assumption here, then my log of P theta X given of Z. So you can think about my X hat is equal to X plus some epsilon right here. And my epsilon actually follows some Gaussian distributions. So this becomes like, as a result, this is something that you already know that from linear regression. This actually has X. And a condition on my decoder theta of my Z and some sigma spirit of my identity. This is another Gaussian. If you look this whole thing right here, this is something that is very familiar. If you and go to this linear regression part, this is actually is equal to minus And we call this as decoder to be x hat, right? So x minus x hat. Square of 2 norm divided by 2 sigma decoder square plus some constant. So forget about all these constant and the stuff right here. Maximize 1 over L of this first part. Is equivalent as minimization of 1 over L. Sorry, then n here. I use n. Of my x minus x hat. Square of theta here because x hat is a function of theta. So that means you have your image using encoder to sample my z, and then map it back with the decoder. The reconstruction part actually trying to minimize the reconstruction errors with from z to the x sphere. So that's why this is called reconstruction function and the construction error. All right, so that's the first part. The second part, which is the KL divergence, that turns out to be easy. Why? Because I already assume my likelihood right here is actually Gaussians. So I'm talking about Gaussians of my Q5 here. P of z is also a Gaussian here. All right, so I'm going to erase this part because I don't need this. So this is a side note that I'm going to use different colors. If you have a 2 Gaussians, say KL of Gaussian of mu0 sigma 0 of mu1 sigma 1. So this is equal to, this is an exercises. It's a little bit tedious, a little bit linear algebra. You can solve it. It's a trace of sigma 1 inverse of sigma 0 minus d. D is the dimension of the data plus u1 minus mu0. It actually has all these analytical solutions that you can think of. Plus the log of determinant of sigma 1 divided by determinant of sigma 0. So with that, we can find analytical solution for the second part. The second part says I have x of I, right? So we need to add them up. The P of Z here. And the D here is the dimension of C's. Okay, so just calculate this out explicitly. Let me just write down the expression here. So this is 1/2. So I want to emphasize this is not the Z of I here because we treat this actually is a distributions here. And P of Z is actually distributions. So KL divergence means I want to calculate divergence between like pseudo distance between this Gaussian distribution and another Gaussian distribution. So this is 1/2 of sigma phi square of my x of I power of d plus mu phi of x of I transpose mu phi of x of I minus d logarithm of sigma phi. And so this is just, we know that as analytical solution, we just plug in and we get this analytical solutions. And the beauty of everything is right here, like, and each term, they are all differential. So you can basically use backward propagations to calculate the partial KL, partial phi, and you can calculate the auto differentiations. And each part right here, it's parameterized by a deep mirror network. Okay, so I have 5 minutes. Let me just summarize everything that we've already done. I want to remind you this picture right here. So this is a very important pictures. Because you will see that in later diffusion models. So the whole variation autoencoder VAE has 2 steps. The first step is approximate this expectation by MCMC. Sorry, by sampling. Not MCMC, by sampling. So basically, the first part is approximated by 1 over n, I from 1 to the n, log of p theta of x of I given 0. And x of I is I training examples, like examples in training, like I images. Think about this. Z of I is exampled with this q theta z given of x of I is actually a Gaussian distributions and we use neural network to approximate the mean and the variances. So this is a like reparametrization trick. So the reparametrization trick is we try to parameterize all these parameters of these Gaussians. The second part is once we calculate this and expectation, then we can actually train the losses. Which is my Argmax of theta and phi of 1 over n summation I from 1 to n, which is basically copying what we already have right here. Logarithm of x x of I, z of I, in the minus KL divergence. X of I and a B of Z. Okay, so should be right. Every part right here is differentiable, so you can use and backward and propagation to calculate everything. So here's a diagram. I mean, this is very famous. If you see it already. So I have X here, and what we go is we pass it in this like an encoder. So this is MLP. What this actually get is not the Z precisely. It's actually to get the mu of X. And another one is log of sigma square of X. Okay. And we are going to be using these two, plus a little bit noise, which is the way that we example. The noise is inject a little bit noise with all three together. Example this. So this is a fundamental difference because in autoencoder, there's no such kind of thing, just like and you apply this decoder, you get a Z directly. But here we are using this an additional like a reparametrization trick to reparametrize this Z using the mean of Gaussian and the log of sigma. Then with the Z, then you apply this decoder. Okay, so this is the function of phi. This is function of Z. And what we got is our X. So you are actually really generating it's like trying to train this and the theta and the phi by feeding all these data and one by one. Okay, that is everything I want to talk about for variation of model. Any questions? Yeah.
You got so long is that
the dark I think dark right here. I saw the dark.
okay, so that's just sampling from processing.
Yeah. Some like samples. This whole variation autoencoder give like foundations for later and diffusion models, and you will see, and a lot of things is very close to each other. So I mean, and once and the most important part is this whole thing right here. We have two part here. So this whole trick is being used applied again in diffusion models in the future. So that's why this is important to and bring this up. At least to have a good refresh of this knowledge. I think this is being proposed almost 10 years. This is a very old models, but has been used widely in the past years. All right. Yeah.
I think it's just I missed something. So you're saying I get you're kind of doing like linear regression, but for the right here, where do the ZIs go again? Because you're trying to
ZI. So
yeah.
See, because Z right here is, I'm actually going to think about this as a function right here. So I mean Z actually and passing this decoder and it becomes its head. So this is a deterministic functions.
Okay.
Which you and this is like and an MLP here. So this is actually and with the Z and that's a function and get the X hat out of it.
Okay, so you sample ZI first and then throw it into the decoder and then.
No, I mean for this part, yeah. So basically, example the ZI right here. You throw this in the decoder here, and you're trying to minimize the and the reconstruction gaps. Yeah.
So when theta and phi are all trained, so you have theta and phi in your computer, how do you generate a sample of X?
Okay, so yeah, that's a good question. So basically, and what you do is you sample the Z right here, right? So and you actually train everything and out of that.
So there we go.
Okay, so so we know, and my prior and the distribution of Z actually follows and the Gaussians, right? But then you can just an example like point.
Oh, okay.
Then you can like apply this in a decoder. But
The Z is you're calling it a prior, and you know that the good model
yes,
is Z is as a Gaussian distribution, and then you apply the decoder function.
yes,
Got the sample.
yes.
Okay.
How much does the dimension of Z matter for like the success of the?
It matters a lot, in fact.
Yeah.
So I mean, so in practice, that's some hyperparameter that you can tune. I mean, you can like and measure the quantities, and it also depends on like so you can think about almost everything in the diffusion model or everything like and you want to compress the information. You want to compress the trunk of data and the information on trunk of data into much lower dimensions. So this much lower dimension is actually embedded in the Z. Z is actually the and give you tells you how much freedom that you can play.
I guess that would be problem specific, like maybe.
This is yeah, very problem specific and depends on images or like and word depends on and what kind of problem that you and want to bring.
I mean, what the actual low dimensional representation would be is problem specific.
Yes.
Sure.
Yeah.
So what are the difference between X and the X hat? Like,
So X, so like X and X hat, it's basically think about this is your like training data.
Yeah.
This is like after you do one forward pass, you got your X hat.
Yeah.
You want your X and X hat to be as close as possible.
Yeah.
Then like you are using this like and the reconstruction to tune your parameter theta and phi.
yeah, I mean, in practice, what does the difference really look like? I mean, is that like in some cases you can perfectly recover X?
No, this is not possible. So like I mean, so like and hypothetically you got a like and a bunch of image of cats.
Yeah.
You feed in like image one by one.
Okay.
Then I mean if you just like and initialize phi and theta like randomly you get garbage. Right? So you get like very large error. Then you want to tune this phi and theta and it's a little bit to make sure this X and the X hat are gradually close.
In the flow diagram, Z goes to X by the decoder, and yeah, up there it's labeled by the probability distribution.
It's the model. So like so every time I write a probability, I just like and specify the model. But when we actually like implement this whole thing right here, it's like and this decoder part is fully like deterministic. I mean it's like NLPG, so you can think about as a like very complicated like and a family of the functions.
Well, could you say how the function symbolized by the decoder block? On your left, you have a decoder block.
Yeah.
Which after it's trained represents a function.
Mhm.
And then up there, the autoencoder.
Yeah.
You have an arrow from Z to X. That's labeled by a probability.
Yes,
distribution.
so this is just a model. That means, the X that I got, like for example, this is, X and that I got, which is my posterior distributions, is approximately by this model right here. So right here, everything there, and the probability of Q of P, they are all the models. They are not the deterministic functions. We need to use and to build this kind of the pipelines to realize these models.
So that diagram on the right represents a probabilistic model.
Yes, just a probabilistic model.
It says that given Z, the model produces random X's
Yes,
with those.
With this
that
distributions. yes,
And the problem is, you don't know.
yes, yes.
You like,
So that's why you need to using this like techniques by injecting, this noise right here.
Yeah.
And like gradually to realize this whole process.
okay, cool.
Okay. We will skip for the next week's lecture because there will be a speaker to give a talk in this seminar. So we will continue after like 2 weeks. All right. So that's the next topic will be the very central core of the diffusion models.